So in this video, I'm going to cover how to convert a sorted list to a binary search tree. First thing I'm going to do is just read over the question. So we're given the head of a singularly linked list where elements are sorted in ascending order, and we want to convert it to a height balanced binary search tree. And there's a couple things going on in this question, right? But one thing I want to cover first is what is a height balanced binary tree? And if you see at the below this photo, I have a brief definition here. Basically what it is, it's a binary tree in which the height of the left subtree and the right subtree of any node does not differ by more than one. And that same idea will apply to both the left and right subtrees. Those must also be height balanced. So for more context about this definition, we see this binary search tree on the right side. And this is balanced. The reason why is because we look at that, if we look at node 3 and we look at its left subtree 2, and then its right subtree 5. We're going to say the left subtree's height, what is that? That would just be 0. And then right subtree's height would also be 0, so 0 minus 0 equals 0. It does not differ by more than 1. And then the same idea will apply to its nodes, right? Its left subtree, which is 2. We look at it, it has null, right is null, so we don't actually have to worry about it. We know it will not differ by more than 1. Same idea for 5. So that's enough context about this portion of it, and now that's enough context about the question itself, and now we can kind of jump into how to go about this question. Now for the approach of this question, what we want to do is try to simulate an in-order traversal, and the reason why is because we know that whenever we do a in-order traversal on a binary search tree, the items we get back are going to be in ascending order. But in this question, we're actually given a singularly linked list, which is in ascending order, which is pretty good because we know we can actually use that information. But the problem is that whenever we do an in-order traversal, we're actually given the root of some tree and we don't have that information. So how we're going to do this is by using, how we're going to build this tree is by using left and right pointers. So we're going to have index 0, 1, and 2. Left will be here, right will be here. Now what I want to do is go ahead and try to build this binary search tree. So I'll go ahead and kick it off by saying build on 0, 2. And another thing I forgot to mention is that we're actually going to have a pointer to my head. And we're going to have a pointer to my head. So once we gone as far left as possible, we know that we can actually use this head node and go ahead and create, start building our tree. So we say build on 0, 2, and we're trying to build a height balanced binary search tree. So we're going to choose a middle index, and this is going to help us build the left side of my subtree and the right side of my subtree recursively. So I'm going to say left plus right, which equals 0 plus 2 divided by 2. What do we get? We end up getting 1. And now what we'll do is make a call to build on the left side. So I'm going to say build on my left side, which is 0. To mid minus 1, so mid minus 1 ends up being 0. And now I go up to my stack frame here and I say let's go ahead and build on 0, 0. When I do this, now I want to do the same idea. Let's choose the middle index again. So we'll say 0 plus 0 divided by 2, we end up getting 0. Now we say build on the left side of my subtree. And one thing to keep in mind is that we'll just have this, we'll save that reference, right? So we'll say left subtree will be assigned to build on 0, negative 1, right? Because we're saying mid minus 1. And now when I've done this, this actually leads me to my base case. We know that how do we know when we're going to stop recursing, right? We're going to stop whenever my left pointer is greater than my right. And when this is the case, we're just going to return null. So now this will be assigned to null. Now I'll go ahead and try to build the right subtree. Or not, actually, before we build the right subtree, what we want to do is actually create this node. We have my tree node, we have my pointer at 1 here. So now we're going to create that node. So we'll say, all right, we're going to create my tree node 1 here. And we can assign it to null, it's the left side, because we found that. And now we're going to try to find the right side. So we'll say right subtree will be assigned to build on the right side. Mid plus 1 ends up being 1. And then we get our right pointer still 0. So we see left is greater than the right, so we get null here. Assign it here, we get null. So we build a certain portion of my tree, and we're going to end up returning this back over here. When we say build 0, 0, we'll say, I'm just going to put 1 so we know our reference is here. Now what I can do is just kind of take this off for now. And now we're going to go ahead and actually create the node next. But before we do that, we had to actually move my pointer. So we have to move my pointer over here. So current is now here. Now we do that, we get this portion is my left side of my subtree, right? And now I create my node. Create node being 2. So I create 2 here, and I can actually assign its left down here. So now it's pointing down here. And now I'm going to build the right subtree. I didn't do this for the left, but what I should have done right here is just kind of put left. So now I'll say my right subtree will now be assigned to build on mid plus 1, which ends up being 2, and then I end up getting 2 over here as well. So whenever I created this node 2 right here, oh sorry, I didn't mean to erase, but whenever I created node 2, immediately after I created it, I want to move my pointer. So I move it over here. So current is now at 3. And we're now making another call to build 2, 2. So we say build 2, 2. When we do that, we choose my middle index again. So we say 2 plus 2, 4 divided by 2 ends up equal 2. And now we're going to try to build the left side. So we'll say left side of this will be build on mid, or left to mid minus 1. So we get 2 to 1, and we see that left is greater than right, so we get null. And then now what we do is we create my node, and I see my current pointer is at 3, so I create my node 3, and now I know this side is assigned to null, so I just put null, and now I'll go ahead and try to build, I'll move my pointer, but it ends up being null, right, because there's nothing over here, so it just ends up hitting, this current ends up hitting null, but now I try to build the right side, and now I say build on 2, or not 2, but rather it's going to be mid plus 1, so it'll be 3 to 2. And then I end up getting null again, because the left is greater than the right, so I get null. And now I return this reference, 3 right here. I'll return this down here, so now this is assigned to 3, and we're going to just choose right pointer to 3, and then at the end we'll just return 2 back up as our answer. So I hope that made sense. There was a lot going on here, but I think as you think about it a little more with the in-order idea, it'll make more sense. Here's the code right now. So here's the code for this question. The first part, I'm just going to go from top to bottom. The first part, we're actually just counting the number of nodes within my linked list. This part's pretty straightforward, so I'm not going to go too much into it. This next part here is where the bulk of the code is. First thing we want to do is get the length, so we use the helper function, or the function above, to count the number of nodes. And then we're actually going to use a pointer called current to point to my head, which will be used within my helper function below. So as for this function right here, what we're doing here is we're going to go ahead and build the binary search tree, and we're going to pass in our left and right index that we're able to find based off the length of our linked list, right? Next thing we have here is a non-local variable called current, which is used to let the stack frames know to reference this variable. And then now we have our base case. Whenever our left is greater than right, we'll just return none. Now we're actually going to choose our mid to ensure that we actually have a height balance, and to ensure that when we're building this tree, we're going to have a height balance BST. Now we actually make a call to build our left subtree. Reason why, this kind of goes back to what we're doing. We're trying to simulate the in-order traversal, so we're just going to go as far left as we can, and once we've gone that far, then we can kind of go back up. Now we create our node. Next part here, we go ahead and move our pointer within our linked list. Now we just assign our left pointer of our node to the left subtree. Same idea, but for the right subtree, we're going to just build our right subtree and then assign our pointer for the right side of our node. And then we'll end up returning our node. And And at the very end, we'll end up just returning the root of this binary search tree, and that will get us our answer. So as far as time complexity, it's going to be big O of n. The reason why is because n will be the number of nodes in our linked list because we traverse our linked list. Because we traverse our linked list, I believe it's twice, but at the end of the day, it'll be 2n, which will just get back down to big O of n. Next thing is space complexity. So we're not using the space that we are using is going to be on the call stack, and when we're using it, it's going to scale with the height of our binary search tree. Luckily, this tree that we're building is going to be height balanced, so it's going to be big O of log n.